We're going to look at why the power rule works and look at it through the lens of f of x equals x cubed. And we're going to find the derivative using the definition with the limit. The limit as h approaches 0 of f of x plus h minus f of x all over h. If f of x is equal to x cubed, this is the function we're starting with, then we could say f of x plus h equals the quantity x plus h cubed. And if we cube that out, that's going to be x cubed plus 3 x squared h plus 3xh squared plus h cubed. I can get that from using Pascal's triangle or any formula, but this is what the quantity is going to be once you have it all cubed out. And this is what the derivative is going to be. So now we can say that this derivative is equal to the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed, all of that minus f of x, which is just x cubed all over h. As you've seen in a lot of other derivative definition examples, x cubes will eliminate each other. Everything that's left in the numerator has an h in it. So if we simplify this down, it's the limit as h approaches 0 of 3x squared plus 3xh plus h squared. That's just dividing the numerator and denominator by h. At last, we're going to take the limit as h approaches 0, and the back two terms are going to drop off as we substitute it in, and we get this expression of 3x squared. Original function and its derivative. Now, this was just for an x cubed, but if you think about this, when you're taking even a higher order polynomial, all the terms are going to have h in them. The original one will cancel out with whatever the original one is you're subtracting with it. And the only thing that's going to be left is this very second term, because when you divide by h, it won't have any h's attached to it. All the other ones will still have an h, so when you evaluate the limit as h approaches 0, they're going to drop off. So this is the one that matters. And the number that's always going to be in this spot, again, comes from Pascal's triangle. It's always going to be what the original exponent was. That's why we can multiply this exponent by the coefficient out front and simplify that down by 1 strictly from Pascal's triangle.